this seems like a really cool organization, and I would be thrilled if I could convince some of you guys to work on the many open challenges in wildlife monitoring that need computer vision, machine learning, um, just like data systems, UI. A ton of effort is needed to scale this stuff up. Wei, are you already recording?
Yes, I started recording right now.
Okay, cool. Sounds good. Yeah, and also, I mean, I planned for, 30, 40 minutes, but if you have any questions throughout, feel free to stop me. And then also I'm really happy to answer questions after as well. So I planned this, basically I'm gonna try to give a bit of an overview of the scope of the problem of, wildlife monitoring or biodiversity monitoring in general. And then go into a little bit more detail on some recent technical advances and approaches that people have tried. And then, hopefully just kind of sow the seeds for all of you to get involved in this really exciting space. So why do we need to monitor wildlife biodiversity globally? Really sort of upsettingly, in the Living Planet report in 2020 by the WWF, they found that we'd had a 68% average decline in animal population sizes in just the recent decades, which is pretty frightening. And it's pretty heavily tied to a bunch of different things that are basically human responsibility. We are drastically reducing habitats at the same time as, increasing the temperature of the globe. And all of these things make it really, really challenging for us to maintain the biodiversity of our planet. So one of the biggest challenges with trying to mitigate this type of catastrophic decline in the species we see globally is it's really, we really don't have enough information about what's happening. Frequently, we find out that an animal is in decline when it's almost too late to really change anything. And then also we need better understanding of how these animals are interacting with us to figure out what approaches for mitigation work, what types of interventions we can do, and then also monitor the effects of those interventions to see if it's possible for us to kind of like scale this up and do our best to reduce our impact on our globe. So ecologists have been trying to monitor biodiversity and wildlife for decades. And up until recently, with some amazing recent advances in technology, making these monitoring sensors much cheaper and sort of much easier to use, it was really only possible to do sort of very detailed studies of biodiversity in really small sort of restricted areas. But as we have access to more remote sensing data, to drones, very, very lightweight GPS monitoring, static sensors, things like camera traps or sound recording, and then also just humans who are getting interested and actually sort of collecting data as community scientists in the field and building these large data repositories of biodiversity data. Our ability to monitor the world around us is really improving. But the challenge is that all of this data is massive. And it's something that an ecologist, when they were monitoring a small network of say 100 camera traps, that's something that it still would take them a year or two to label all the data, but it was scalable. But now when you're looking at, hundreds of thousands of camera traps around the world, it's no longer really possible for humans to do all of that labeling. And that's where these machine learning technical advances come in, where we can actually automate the data processing for all of these different pipelines and potentially start moving towards trying to build this global real-time picture of biodiversity. But unfortunately, unlike your sort of classic ImageNet or Microsoft Cocoa example, where the data is taken by humans the majority of the time, a lot of biodiversity data can be quite noisy. So the thing you care about might be really hard to see, like this giraffe behind a tree. We have to deal with poor data quality, things like weather and bad lighting. And then also, unfortunately, because of the sort of constant monitoring that a lot of these sensors are doing, you get a lot of data that just doesn't have anything in it that you care about necessarily. And these are kind of challenges that that general machine learning, some approaches do have to deal with this, but most of the time it's not to this extent. And then also, biodiversity data by definition has a really long tail. So what you're looking at here are observations in iNaturalist, which is a community science platform. And what you see is that, if you need to get around 100 examples for a machine learning model to perform reasonably well on a species, which is a reasonable rule of thumb. So we've got, around 10,000 species that have 100 examples, which is pretty amazing. But there's another, order of magnitude or more species that have much less than that. And so what that means is that basically your machine learning models have to learn to deal with this data imbalance, but also we have to figure out how to handle the low data regime to be able to do well. And actually, interestingly, in the biodiversity case, those species you have very few examples of, those might be the ones that are sort of at most risk, the most endangered or the rarest. And so those are actually the species you really want your models to perform best on in some ways. And then also, biodiversity is just not IID. The underlying assumption of a lot of machine learning is, and especially deep networks, is that you're training your model on a representative data set, a data set that has sort of the same underlying distribution as the data you're going to be testing the model on. But with biodiversity data, or sort of any data that's collected around the globe, what you find are there are these very strong correlates, or these very strong sort of non-IID distributions that are based on where and when the data was taken. And so that means we need to have models that can kind of handle this type of non-IID data, be able to generalize outside of potentially the distribution that they were trained on. So one example of this type of sort of location bias is looking at static cameras. So this is one very common type of sensor that ecologists use to monitor animals. And they're mostly used, at least camera traps are mostly used to monitor medium to large terrestrial mammals to the most part. So what you can see here is, so this is data from Wildlife Insights. And Wildlife Insights, I work on the AI team for them, but it's basically an attempt to scale up and build robust machine learning and data management systems for ecologists that use camera traps. And so globally, there's thousands of organizations using camera traps, tens of thousands of different projects within those organizations. Each of those projects has entire networks of camera traps. It means there's around millions of camera traps that are actively being used, and that results in hundreds of millions of images. So you can really see the need for machine learning here. And so, for example, one of our collaborators, the Idaho Department of Fish and Game alone, when we first started working for them, they had 5 years of data that they hadn't been able to deal with and hadn't been able to process, around 5 million images. And that's actually gone up since then. But also, on average, 70% of the images from any of the cameras are empty, right? Like we talked about before. So this is like a pretty serious thing you have to be able to handle. You have to be able to not give false positives on these empty images, but also you don't want to then give the ecologists a ton of incorrect predictions or miss animals that you care about. So it's pretty important to kind of fix that trade-off appropriately. And then what you have here, and this is kind of like that IID thing, every single static camera has its own distinctive background, so its own distinctive sort of pixels that are somewhat fixed, as well as its own sort of micro habitat of species that you see, its own distribution over the class set. And the reason for this is that animals are actually very habitual. So here, these images were taken a month apart. And what you can see is that this deer, is just sort of coming back. This is some type of game trail, some type of thing. And these images, for images that are a month apart, look very I got muted for a second, but okay. Can you hear me now? We're good?
Yes.
Okay, awesome. And so what this causes is this causes the models to to kind of be able to memorize what's seen at a given camera trap or at one of these static sensors. Um, and it also means that the sample efficiency of the data, you have those hundreds of millions of camera trap images, but the amount of variability you're getting from the images within a single camera can be very low. And what this causes is this causes a big drop off in performance when you go to new cameras. So, for example, you can train a machine learning model, and it will perform quite well on the camera traps that you've actually trained the model on. And what you see there, so that's the error. This blue is the error curve there. Now you do also see just sort of across the board in machine learning, you see that the error when you have very few training examples, like 1 to 10 to 100 can be a lot higher. Whereas, if you have a lot of training examples, your error can be really low. But this then jump in error across the board that you see when you actually evaluate the model on camera traps you haven't trained on, this is something that we're trying to do. We're trying to fix. We're trying to close this gap, this generalization gap to new cameras, because basically ecologists are putting out new cameras all the time. And if we can't fix this problem, then what that means is that we're going to need to retrain whatever machine learning models we have on every new camera people place. And this type of distribution shift and that corresponding drop off in performance is pretty ubiquitous in real world scenarios. And so I worked along with many sort of amazing researchers in the last year to put together a larger benchmark of real world distribution shifts across many different types of real world data. And so if you want to go check it out or try the benchmark yourself, it's this WILDS data set on the website's down here. So one thing that we did find actually helps a lot in that static camera scenario. And, it's somewhat unsurprising, but if you can just reduce the impact of the background features in your data by just doing straightforward detection instead of image level classification, that does help you sort of learn to disambiguate foreground and background, and it helps you generalize a bit better. And what we also found that was very interesting is that though the classification part of the problem generalizes pretty poorly, and even with localization, there's still a big gap. We saw a much smaller gap in generalization for just localization of animals. So a couple of years ago, I worked together with Microsoft AI for Earth, and we built what we call the mega detector, which is basically just trying to solve that problem of filtering out all of the blank images to try to help make the humans, the ecologists who are working with the data, a lot more efficient. And so this is, it's being used by over 30 organizations globally and being queried, a couple 100,000 times a day even. But this is just two examples of different organizations that are using this model in their ecology workflows currently. So one is the Idaho Department of Fish and Game, and they're using this, just one of the projects they're using the mega detector for is wolf population management. They have 2,000 cameras that are out there basically looking for images of wolves. And those collected 11 million images last year alone. And this year they're actually scaling up to 3,000 cameras, so it's going to be even more. And so by using the mega detector, which just detects animals, humans, vehicles, or lets you know if something is empty, they were able to restrict the number of images they actually had to review by a human down to 15%, which is really this was a huge deal for them. And then the other example where this is being used is with Wildlife Protection Solutions. And so Wildlife Protection Solutions does real-time wildlife crime prevention. So what they do is they actually have the mega detector running in the cloud, and then they've connected their cameras on the edge to the cloud so that they're actually sending images that are in real time pinging our publicly hosted API. And then if they catch vehicles or humans in protected areas where they think potentially they're not supposed to be there, then they send real-time alerts to the managers of those protected areas. And this is pretty vital for things like catching potentially poachers or people who are doing things like illegal coal burning. But so this is great. We're already able to make an impact. We're already doing something that's seriously helping people scale up the way that they're interacting with wildlife protection and wildlife monitoring. But we still haven't solved the problem, right? I mean, humans still have to look at a lot of the images. And part of the problem is it's just like when human experts are labeling this data, they're able to label some of these really hard images. And it's things like this where, like, I don't know, that's really, really difficult, right? So we look at it and you're like, oh, okay, maybe there's something here. It looks like maybe it could be an object. But from just this image, there's just, you don't know if that's a tree, like you don't know if it's an animal. It can be really, really difficult if you just give a human single images at a time, which is kind of the normal framework of machine learning models as they look at single images at a time. But what humans are able to do is they look at the data over time and they look through a lot of images from the same location. And so from that, you're able to tell like, oh, okay, well, I can't really see in this image, but in that image, I can see that the horizon doesn't have any trees. So any of these sort of blobs that I'm seeing here must be animals. And then you can also see that there's really frequently these herds of wildebeest that look approximately the right shape or the right size to match what that is. And there are herd species and the other herd species in the area don't look similar. And so that all of that context, that implicit context that they're getting from not just looking at like, a minute of information, but actually looking over the entire, like an entire month of data, for example, that's helping them identify these really challenging images. And so what we try to do is we try to basically see if we can like do what the humans are doing. So humans are using this temporal context to improve the per location object classification, right? So, hey, if you're seeing things across time and in one image you can be very confident about the species, you can probably propagate that confidence in some way to these other more challenging images. And then it also helps you understand when something is likely to be foreground or background, because it says like, okay, look, this thing is always here. Probably it's not an animal, right? And so we tried to bake this into machine learning models. And so the way that we're doing this is we do sort of a first pass where we build up this representation of everything that's seen at a specific location. So what we do is we, extract features from different objects seen over time. We reduce that feature size. You kind of curate the features. So we don't, keep everything that's detected in every image. We just keep a few examples. We also maintain spatiotemporal information, like where in the image was this thing? What day was it taken? What time? And then we essentially then inject that as additional information using an attention block. And I'm sure if you guys are, following machine learning, you know how popular attention has been in the last year. But in this case, it's kind of a pretty wonderful tool, because what it allows you to do is attention allows your model to decide whether the other things it's looking at are relevant and choose to pay attention, literally, to the things that are most relevant for improving that decision. And so what we've done is we basically just take a faster RCNN model, which is a two-stage detection model where the first stage tries to find things it thinks are objects, and then the second stage tries to categorize those objects into one of your classes or empty. And what we've done is we just injected this pre-extracted feature bank here via an attention block. And we basically say for every object that we've proposed with the region proposal network, you just say, okay, well, here's that object. And now we build this contextually aware vector that says like, okay, projects the object, projects all these features, and compares the similarity in some sort of reasonably comparable space that we've learned by learning these projections and in the attention layer. And then it just says like, okay, what is most relevant for me? And I'm gonna keep that. And we do it recursively. So you still get the original object features as like the strong signal. And what we see is by doing this, we really see a lot of improvement predominantly on those challenging cases, like what we were discussing before, right? So things or the objects are like moving out of frame, where, you know, like the thing that we care about is highly occluded or dark, that's where we're seeing that this context approach is really helpful. And it also does help reduce the impact of these sort of what we call background distractors, these sort of salient false positives, stuff like that rock in the previous example. And we do actually correctly label these really challenging objects by taking this context approach. And there's pretty much no way that you could do that otherwise. And I think another point that I hadn't addressed yet, so you might look at this and say, okay, well, why don't you just use like a video approach? Why don't you use one of the things that people have already been doing to incorporate temporal information, like from video? And so we did try, right? And we have those benchmarks in the paper that I'm discussing here. But the problem is a lot of those video approaches assume spatiotemporal consistency. They assume that the frame rate is going to be some reasonable amount where you can kind of, you know, you have some sort of temporal consistency across frames, either explicitly or implicitly. But camera trap data, it's taken on a motion trigger most of the time. So that means you can have some images and then none for hours. And then also when you do capture images, the frame rate is never much higher than 1 frame per second, unless it's explicitly a video camera trap, which are becoming more common. But for now, you know, all of the data that we're working with, you have this really low frame rate and it's a variable frame rate. And so by taking an attention approach, you're basically, you remove any sort of heuristic requirements on the frames being relevant or not. And so the other thing we see is, you know, like I said before, like it's temporal, it's adaptive, right? So in one case where you have a warthog that's sort of taking that same game trail, and all these images are spread out across the entire month of July, but you can see how similar they are, right? It's able to aggregate information from these different examples across this very long time horizon. Whereas something like this Thompson's gazelle is just hanging out in front of the camera for a few hours. Sometimes the animals do that. Then you have tons of images of that actual individual instance, and the model decided that those were actually the most relevant. Yeah, so context is super helpful within a single static sensor. And what we find is it actually helps us generalize as well, because it's giving you this representation of what's seen without actually needing to train on a new camera, right? You get to kind of, it's almost like an unsupervised adaptation in a way. But can we go even farther? So the next question is basically like, look, I showed you all those different types of sensors that people were using, right? And you know, here's some examples again, like camera traps are what we've been talking about, but you know, we have tons of satellite information. You know, all this information that's being collected by these community scientists going out and taking photos around the world. And each of these types of data are complementary. Remember I said camera traps focus on medium to large terrestrial mammals, mostly just because that's kind of the way they've been designed. Well, that's only a really small part of the taxonomic tree. People have shown that you can actually detect whales and elephants in satellite data, which is really amazing, right? But that's not going to work for small animals, and it's definitely not going to work for things that are under tree cover. And humans are an amazing resource, but humans go where humans can access, right? And I don't know if you remember that heat map I showed way back at the beginning, but the most biodiversity in the world tends to be where humans aren't. And that's, you know, kind of, that's something that we don't want to change. We don't want to necessarily be sending armies of humans into, you know, areas that are reasonably protected just by being inaccessible. So the right approach for sort of really building this global picture is going to be something that is able to bring together these different types of data and potentially share information across them to improve the way that we're processing the data. So this is what I'm talking about, right? Here is an example of all the iNaturalist observations. These are all in the Northern Hemisphere, the huge bias towards Western countries. Satellite data gives you this really nice global coverage, but the resolution is super low, and the temporal resolution, though it's getting better and better, is still like, it's not the same as having sort of this constant real-time monitoring. And then, you know, camera traps you can actually take your network of these remote sensors like camera traps or even like GPS collars or something, you can put them in these areas where humans aren't accessing to kind of like cover those gaps. Now, this is something that I think is really where we're going to need to go to be able to build the type of monitoring systems that we need to be able to protect our world. But these are really, really interesting and very much still open questions. So last year, I do this yearly competition where we try to build interesting machine learning challenges that will answer these necessary real world questions with camera trap data. And so last year, in addition to just providing the camera trap data, we also provided satellite tiles for each of the camera traps with the hope that we would be able to start building models that are actually able to learn to take context maybe from not just the images within one camera, but these satellite images. And this year we've extended that competition even further to answer a new, very challenging ecological question. So we took that same data, you still have access to the satellite tiles, you have access to iNaturalist data from all over the world covering the species of interest. So you can try to learn this cross-domain or domain adaptation thing where you get, human captured images and camera trap captured images. But instead of just asking people to categorize the species, we're asking them to categorize them and count the number of individuals of each animal seen across a sequence. So detection will give you like, this is how many animals we think are in this image. But part of the problem for ecologists is that they need to be able to estimate a population size. They need a sense for, okay, but how many gazelles did you see? And if you see 5 gazelles in one image and 8 in the next and 7 in the one after that, what does that mean? How many were there total? And so this is something that I think is pretty hard. I mean, looking at these kind of challenging examples from the training set, you can see how tricky that can be. But I think it seems like a really exciting challenge for machine learning. And so I'm very excited that, that this is what we're trying to do this year. And we've provided this benchmark for people to take a crack at this challenge. So thank you for having me. And I'd love to let you guys know more. I've been teaching a class at Caltech this last quarter where we're having advanced computer vision students tackle these types of problems. And for that class, I built this huge list of projects to help sort of seed people and providing data sets and pointers. And so if that's something that this community would be interested in, I'd also be happy to kind of connect you guys to that, because camera traps are only one tiny bit of the problem. There are so many different types of data and so many different questions that need to be answered.